Hi, everybody, and welcome to another recorded Zoom session with Jeff Tepper, University of Puget Sound. And Jeff was featured in yesterday's Breakoff Belt Magma session, and we're doing another Breakoff Belt Magma session tomorrow morning with the alphabet, Cascades A to Z. Jeff, what's the weather report in Tacoma this morning?
It's not raining,
It's not raining. Oh, wow, it's not
but it is
raining.
forecast to rain for about the next 10 days.
Even over on
It'll
this
be
side, it looks like
it'll
that's the
be a wet
case.
Christmas.
Yes, yes. Wet even over here. No snow for us. So whatever. Um, Thank you for your time again this morning. I think what I'd like to do with this conversation is share some chicken scratch, some kind of roughed out sketches that I have in mind, and that might lead us to some of the detailed geochemistry that you can help me here with. And then I'd want to use some of it tomorrow morning. So thanks as always
Okay.
for your time and expertise. Let me share my screen. We'll just go right for it. If you're watching, viewers, if you're watching this recorded session and you have no context for this, I'm afraid we're just going to talk like you've seen the break-off belt, the break-off belt magmas that we were talking about last time. So this is a little inside baseball, but I want to get right to the expertise that Jeff has. Here's my thought, Jeff, and you can jump in wherever, and then I'll ask some questions specifically. But this is my plan,
Okay.
I think, at least at this first pass. I want to go back to these cross sections I was drawing 3 letters ago, where we have the basement in gray and grello, and we have the swak on top in orange, the Arcosic sands and muds.
Right.
And we bring in Siletzia 51 million years ago, and then in cross-sectional view, to kind of take Ken Clark's break that we were looking at with his beautiful colored pencils, but emphasize that we're getting these break-off magmas to come up through the grello and I guess up through the swak. Are you visualizing these break-off magmas coming up through the swak? Has that ever occurred to you?
I hadn't thought about it, but time-wise, the SWAC began before the breakoff belt, so there should have been
Yeah,
at least some initial deposition in those basins for the breakoff magmas to pass through.
you'd think, and now I'm remembering that no, not that. That I even had those black chert pebbles with the rivers flowing away from the accretion. So I
Right.
even had, okay, well, that's a thought. Hang on, hang on. So that's one of the things we're trying to do here. New thoughts that just kind of come out of thin air. That's a new thought right there because in the last sketch that I made, I had lifted much of Grello to the surface to get those black church to be sent eastward. And maybe we have, by the time we do the breakout stuff, maybe we have uplifted and eroded a bunch of that swak. I don't know. Like, I don't know if there's enough time to do that really, but um,
Well,
you don't have, go
you
ahead.
pointed out last time that the basalt of Summit Creek is associated with the sandstone of Summit Creek. And I don't
Yes.
really know if the sandstone of Summit Creek is correlative with the SWAC, but it's in that time slot.
Thank you. Okay, so I'm going to try that. Whether that gives us more dividends or not, I'm not sure, but we're emphasizing time-wise the difference. This is, I think, the theme that I want to establish using geochem, but any way we can to establish the difference between the lavas that are pre-volcanic arc versus volcanic arc magmas. Um, I think I want to also try to draw this, which is a little bit more direct with many different block diagrams and other things you've had in your posters that I've seen over the years, that the breakoff belt is tied specifically to Siletzia. So if we look at a map, as I indicated yesterday in that session, don't we need those breakoff belt magmas to go all the way down to the southern margin of where Siletzia is offshore in southern Oregon?
We would expect that to be the case.
Yeah,
But the issue in Oregon is that there's a lot of young volcanic rocks that are
right,
on top of. So, we have more uplift in Washington, and so
right.
there's less of an issue with younger rocks obscuring what might have been there, the Eocene.
couple of the folks, I did see the replay of yesterday's show and I did see the live chat. A couple of folks got excited about the Clarno, and I know that you've had the Clarno on a couple of your posters. Are we in the right time frame for
Uh,
protect? The
I think
Clarno could be Breakoff or not?
I don't understand the Klarno very well.
Yeah.
It is sort of in that it's older than what we would associate with the Cascades.
Huh.
Um, I don't know
Yeah.
enough about the Klarno to answer that very well. It was on some posters we generated a long time ago because
Right.
fortuitously or not, its location seemed to sit on top of a slab window, which would have been the southern margin, the southern boundary of the rollback.
Okay. Well, that spurs another thought. A surprise to me from yesterday, and thank you for being in the live chat. And I noticed you were answering people's questions during the episode. That was fun. I don't know if you're going to do that again tomorrow or not, but that was a nice plus. Um, so many people have been watching many of these episodes with you and others in the past that they wanted to get right into the excuse me, they wanted to get right into the slab window and the slab gap and the rollback, and they were ready to involve all these things at once, which I don't know if this is a disservice to just chisel out your Breakoff story and not have it connect with these other things, but clearly people want that to happen. If I go back to that image, what if it's a three-ring circus that you're offering, Jeff?
Okay,
Breakoff, rollback, and initiation.
right.
And I think we're going to cover all three. Are you seeing more than the Breakoff with this map if I do it this way? Are these the two tears to allow your rollback to happen?
Those what you labeled tear there would be the northern and southern boundaries of what rolled back,
Yeah.
and they conform pretty well to the northern and southern limits of Siletzia, which makes sense because if Siletzia stops moving, once it reaches the margin and is accreted and is not subductible,
Yeah.
whatever is to the south that was originally the other portion of the Farallon plate that keeps going, there has to be some kind of separation between what stopped moving and what's still moving, and that's that what you've labeled as a tear there at the southern boundary, and the northern tear corresponds to the slab window that would have separated the Farallon plate and the resurrection plate in
Yeah.
Spencer Houston's work. So you do need something that delineates the northern and southern extent of the rollback, and I think that's what you've got there, those two tears.
Good. So that's more reason I think maybe to do this, because we can keep coming back to this and say there's more that we're going to get out of this map from just locating the position between the Siletzia suture and the Breakoff belt, but we can then take it a step further, but we have to be patient. We're not going to do it tomorrow.
There's one
Um,
other, can we point
yeah,
out one more thing? So
please.
the dashed line there that you've labeled Breakoff belt
Yeah.
is shifted to the east from Siletzia.
Right.
And so I would say, in my way of defining things, the line at the eastern edge of, okay, that line is both the Breakoff belt and maybe the limit of Siletzia in the subsurface. So
In
a
the
portion,
sun.
so
Oh,
remember, Siletzia was jammed under the edge of the continent.
right.
So I would make a distinction. I would call the green line you just drew, that to me is the suture, because
Yeah.
that's what you might see at the surface, although it's not very well exposed. But the suture and the easternmost extent in the subsurface, to me, aren't the same thing.
Okay. That's helpful. And that's what the Ken colored pencil drawing shows. There's
Right.
that. Yeah. Okay. I'll emphasize that tomorrow. Thank you. Okay. Um, what do you think of this one? Where we're starting to then get into the detailed geochemistry of the melts. And I'm again just trying trying to set up the difference between melts generated
Mhm.
by Breakoff versus melts from a normal volcanic arc. What would you and times here? what would you add to this cartoonish view? Is this truly decompression melting? Is that the right phrase to
That
work with?
is.
Okay, so this is
Yep.
solid mantle that's losing pressure, so it's becoming solid and becoming liquid. That's the only major change, just the pressure
Right.
as it rises,
So that's hot mantle coming from below the slab,
which is solid mantle.
which is all solid.
Yeah.
So that's called the asthenosphere, the part of the mantle that's below
Okay.
the plate. And if you bring that to the surface, it will spontaneously melt because of a decrease in pressure.
Decrease in pressure. Good. Um, and I just stole this from Ken's cartoon saying
Yep.
water vapor. That must have been you. Am I correct at the most basic level that we have water inside of this downgoing slab? The water's
Right.
being um, forced out of the
Yep.
downgoing
Yep.
slab,
Right.
and we're adding water to the base of the crust. We add water that lowers the melting temperature. We create melts.
Right. Although you're actually adding it to the mantle, the piece of mantle that's called the wedge,
This is the
that's the mantle wedge, right? So it's above the plate and below the continent, right there where they're coming together. That triangular shaped piece of real estate
yeah
is the mantle
that
wedge. And you're adding water to that
yeah
from the slab, and that triggers melting of the wedge, which produces
okay.
basalt, and then basalt goes up into the crust. So those are the two
Good.
fundamental ways on Earth that melting in the mantle takes place, either by decompression or by adding water.
Thank you. And so to me, that sets up what I think are the three main ways to synthesize what you wrote to me in the letter. The breakoff belt magmas have bimodal signatures. I might do a quick igneous rock classification chart and emphasize that we're on both ends of the spectrum.
Right.
The spidergram thing, which I'm trying to get some help from you right now, the triangles. And just before we dive into that, are the are those the three main ways to try to are those the three main approaches to you're looking at a melt and you're trying to decide between break off and arc in this case, those the three approaches, the bimodal, the spidergrams and
Diagram
the
and the
triangles?
AFM, right. The only one I would add is isotopes, which are they're a fingerprint for whether you're melting the crust or not.
Okay.
And I didn't send you much about that.
Okay. Shit. Sorry, Patrick. Oh, come on. Okay. Good. So bimodal, I think I can handle. Yeah, but the other three, I need some help. So let me guide you here. And so this letter now, the viewers have, and they'll have a chance to study it over and over and over again. Can I summarize quickly and then see what I am not understanding?
Yeah, sure.
Okay. Are these rare earth elements or not?
Not all of them. Those are just a
Okay.
suite of trace elements, elements that are in low abundance in rocks.
I know how to pronounce rubidium, barium, thorium. How do I pronounce this?
Tantalum.
Tantalum
Hmm.
and niobium.
Correct.
Okay, look at me. Uh, I think you're saying, and it's tricky because I think this is the part where you go, not always. This isn't like a cardinal rule. It's like I want things to be black and white, and I know we've got shades of gray here, but this is the approach with the spidergrams to say it's really just looking at the, oh shit,
Yes. All right.
tantalum and niobium.
Right.
You're looking at, do we have a depletion or are we nice? We have a lots of those two
Okay.
guys.
Can I give a little background to
Please
this
do.
diagram?
Yes.
All right. So um, all the things we're going to talk about this morning are based on chemical analysis of a rock, knowing what elements are in it.
Good.
And so this diagram is using elements that are not very abundant, trace elements. And so
Okay.
there are a bunch of different elements across the bottom. And the takeaway here is going to be that this is a tool for just establishing what tectonic setting a magma forms in. And by tectonic setting, we mean, is it an arc? Is it a hot spot? Is it a mid-ocean ridge?
Thank
And
you.
so you take the element abundances in your sample and you divide them by the average abundance of those elements in a mid-ocean ridge basalt.
Oh, yeah, yeah, yeah.
Okay,
Right.
so that's what on the side there where it says sample over morb. Morb is short for mid-ocean ridge basalt.
Good.
So if you took an average, if you took a mid-ocean ridge basalt and divided it by itself,
Right.
you'd get a horizontal flat line on this diagram.
Yeah, I'm with you.
However, if you take a sample from an arc, a subduction-related rock, you get a different pattern, and you get the pattern that's shown here. And the two notable features are that there's a hump at rubidium, barium, and thorium,
Yeah.
and there's a valley or a depletion at tantalum and niobium.
Hmm.
And that's just true of all arc rocks. You would like me to make an absolute statement? That's as close as I'm going to get is
I
all
love it.
arc rocks. Okay, so
I love.
it's makes me nervous to say all, but it's pretty
I know.
widespread. Okay,
And
so
and we're in the Cascades, and so the Cascade arcs. We're not talking worldwide now, but the Cascade arc rocks typically have this pattern. So
right,
most of the take your favorite Pluton that's younger than 46 million years, or the andesites in Mount Rainier National Park. They
they have
probably have
all,
this
yep.
signature.
And in
Good.
every arc worldwide, this is not special for the Cascades.
Good. Okay.
Okay, so this thing is called a spider diagram or a
Yeah.
spidergram,
Okay.
and our goal is simply to collect a sample. Each line on that diagram was a different sample. So when you use this, you have to have all those different elements as part of your analysis. And that was what was lacking from a lot of the early work done in the Cascades is they didn't measure these elements.
Right.
So we couldn't make this kind of diagram.
I'm hung
So
up
we
on a
made,
detail. Are these five trace elements?
everything on there is a trace element,
It is. Okay.
right? So by definition, a trace element has a concentration of less than a tenth of a weight percent.
Okay. Very good. But they're on the periodic table. They're
Everything
just,
on there is
yeah.
on the periodic table. Yep.
Okay.
And some of them are rare earths, but not all of them. But they're
Okay.
all trace elements.
Okay. Very good. So we're leading to the idea that, oh my God, we've got some of these magmas in the Cascades that are older than 46 million years old. And some of them have a hump instead of a valley for these two rare earths, trace
Yes,
elements.
so some of them it has a sort of smooth hump pattern that has a peak at rubidium, barium, thorium, but then it's just sort of smoothly declines the rest of the way to the right.
Yeah, like this, maybe.
Yeah, you
No.
can make it. Well, yeah, that's okay. Just you still have a sort of a hump there, but
Oh, okay. It's kind
but
of a, yeah, okay.
so
It's not this.
if you made it convex, you just made it.
Oh, like this?
Yeah, and take it
Okay.
all the way to the end.
Okay. Okay.
Okay. All right. So the approach would be to, analyze some samples. And if we have some samples from one of these units that we think might be part of the breakoff belt, and
Yeah.
it does not have that valley at tantalum and niobium, that would be consistent with that's a magma that didn't come from a subduction. That's a upwelling through the tear in the slab or the break in the slab magma. That's an asthenosphere derived magma.
This is perfect. This is just what I was hoping for. And I'm checking in with the viewers, and you're like, I'm lost. What's going on? Well, if you didn't see the last episode, I explained that 20 years worth of Jeff Tepper's students have produced abstracts and posters, and all of the breakout belt magma posters and abstracts are at my website, nickzentner.com. Click on the word Cascades, and I just in the last hour put a bunch more for tomorrow morning's episode. So all the breakout belt magmas, abstracts, and posters, especially the posters, almost every one of those posters has a spidergram.
Yep, that was one of the major lines of evidence that we could we could make that measurement on campus or, samples we could analyze. So
Yeah.
yeah, that was almost every poster is going to have spidergrams.
And why was that impossible 30, 40 years ago to to make a spidergram like that?
Not impossible, but the analytical instrumentation has improved dramatically. So there's new analytical equipment, and the old ways of measuring those elements were just much more tedious, expensive, fewer places that you could do it. So, now we can't do all those elements on campus at UPS, but we can do a lot of them, and then you can send them out, and for $50, you've got an analysis as opposed to, used to be done, you had to put your sample in a reactor. I mean, it was a very challenging type of analysis. So it's all about having, easier access to the analytical equipment.
And who trained you to do that work with spidergrams?
Um,
Or
well,
did you
Tony
teach
Irving at
yourself?
the no, Tony Irving at University of Washington was on my committee when I was a graduate student. And I actually remember they were just developing spidergrams, in the 80s. And
Huh.
it was a question of, in what order do you put those elements? Because, there's a bunch of them across the bottom there, and they're not ranked by, atomic number or something. They're ranked for other reasons, but different diagrams will have the same purpose,
Yeah.
but different people have used different elements and in different order across the bottom. I like this one because it's doesn't have too many elements and the patterns you see are smooth,
Good.
but other people use different parameters.
Okay. Well, unless you feel like you want to add something, I feel like that's a great guide to then going to the student posters for our viewers. They know how to read the most basic message about arc or not arc based on the humps and the valleys, the peaks and the valleys that you just mentioned. Anything else to add before we move on to the triangles?
No, just that the thing we were looking for when using this as a tool for assessing is this part of the breakoff belt would be, are there some magmas there that don't have that arc signature?
Yeah. Yeah. Okay. And you found a bunch, and they have that beautiful geographic pattern. Um, is this as important, or do you like the spidergrams? Are the spidergrams more useful and more powerful than these AFM plots?
Spidergrams are a little more powerful because spidergrams says arc or not arc.
Yeah.
This one's is not as definitive because
Hmm.
if it's in the bottom, so we can talk about how to plot this in a minute if you want, but if a
Sure.
sample, each point on that triangle is a different sample.
Okay.
And if the sample plots in the lower half there, which is labeled calcalcal, then it's an arc rock.
Okay.
If it plots in the upper part, it could be an arc rock, but it doesn't have to be.
Oh, I kind of like this then. I made a good call there, huh?
You're right
Yeah.
on.
Okay. So
However,
it's
so
the triangle is a confirmation that you have an arc magma, but it's not necessarily a confirmation you have breakoff.
correct.
Yeah.
Um, if so, there are rocks in the Cascades which are part of the arc. Clearly, they're young and they
Right.
classify as tholeiitic. But most of the time, when you see a tholeiitic rock in an arc, it's either that the arc is young, it's an immature, so subduction
Ah,
started relatively recently, or the crust is thin.
yes.
So we would expect to see more tholeiitic compositions among early Cascade rocks than among later Cascade rocks.
Hmm.
But
Okay.
it's just not quite as, you could also have mid-ocean ridge basalts are tholeiitic and hotspot lavas are tholeiitic. So
Sure.
the tholeiitic category is more inclusive.
Okay. And then the last one on our list of approaches to say arc yay or nay is isotopes. Now you're going off the board. I have no idea what you're about to say, but can you fill us in? How would you describe this isotope work to be? And it seems like you're pretty excited about the isotope work. Like
There's,
that's a good
yeah,
tool.
yes. I could guide you in drawing a diagram. Do you think that's too?
No, let's do
Adventurous?
it.
All
Oh,
right.
you're gonna talk. You're gonna coach me
Why
as
don't,
I draw.
yes.
Cool. Okay.
Okay. So,
Let me get a blank piece of paper. I love this. This is fun.
okay. So we start with a clean piece of paper. Okay.
Right up, boss.
All right. So draw a rectangle which is wider than it is tall.
This is like a game show now. This is good.
We'll see how this goes.
All right. Wider than it's tall,
Right. So, maybe it's 2 inches tall and 3 inches wide or something, or
like a
a,
box.
a box, a rectangle that's wider than it is tall. Perfect.
Cute.
Okay, now draw a crosshairs on that. So a vertical line and a horizontal line that's offset. So let's draw the vertical line first. And let's make it 1/3 of the way across the diagram from the left. Perfect. And now let's draw a horizontal line, which is 2/3 of the way up the diagram.
It's a map of
Okay,
Albania,
that's
flag of Albania.
all right. This is
All right.
perfect. Okay, and we're going to label the axis on the bottom 87 SR, and then a slash, and then 86 SR.
Son of a gun.
You already know where we're going.
Kind of.
Okay, and on the y-axis, the vertical axis, we're going to label it, um, make an E, capital E, and then a little subscript, capital ND. Perfect. Okay, so those are what we're going to draw on here are the isotope ratios of two elements. Strontium isotopes is on the x-axis, and
Okay.
neodymium isotopes are on the y-axis. And that's NEO.
I
Do you
do it
want
over
to?
here.
No, on the it's the vertical axis.
Vertical is N.
NEO DYM IUM. Okay, so neodymium is an element that also has multiple isotopes. And that E is just a shorthand way for talking about them.
I see.
Okay, so the important point about
I just
isotopes is that different places in the Earth have different ratios of these two isotopes.
okay.
So the crust is different from the mantle on isotope composition. But when you melt something, the melt will have exactly the same composition as what was melted isotopically.
Hmm.
So the analogy is if you melt chocolate ice cream, the melted chocolate ice cream is still chocolate. It doesn't turn into mocha.
Mhm.
All right, so in that upper left little box, that's where the mantle plots.
Okay.
So you could put an M or you can label it mantle or something like that. All right, and in the lower left, that's where lower right, that's where continental crust plots. And you could draw then a sort of broad line or swath that goes from mantle to continental crust. It'll be a sort of a line that sweeps across there, and you can make it, several strokes wide. That's it. Perfect. All right. So most rocks on Earth, if you analyze their composition in terms of these isotopes, they'll fall somewhere on that line. All right. So most rocks in the Cascade arc are going to plot up in that mantle corner because they're coming out of the mantle,
Hmm.
and they may interact with continental crust a little bit, but that doesn't affect them very much. So
Okay.
modern Cascade arc lavas mostly plot in that upper left quadrant.
Okay.
And and that's where basalts in general, anything that's coming out of the mantle and is not contaminated somehow, will
Right.
plot in that upper left corner.
Okay.
And what was distinctive about a lot of the Breakoff magmas was that the basalts plotted up in that upper left corner, but
Yeah.
they're bimodal, and the crustal stuff, the tuffs, the silica rich, the rhyolites,
Yeah.
they define this swath that goes off toward continental crust.
Got it.
So
Okay.
this was our piece of most unequivocal piece of evidence that in a lot of these bimodal rocks, we were seeing crustal melting
Hmm.
of older crust, not just, the remelting some new stuff in the arc, but melting something which predated the arc.
The terrains.
Yes. Yep.
So can I
So
write, so can I write basalt and rhyolite like
you
there and
could,
there?
or you could make a little oval up there in the upper left and call that Cascades. So it's, it could, yeah, that's perfect. So it can extend across that bullseye. And you did, perfect.
Okay.
And that's Cascades.
Cascade arc.
Cascade arc, yes. So subduction related, younger than 46. And then you could put Breakoff belt as a similar oval, but very elongated so that the one end of it overlaps to Cascades, but no, it's going to go all the way to the
Oh,
Cascades. It just has a much bigger range. It goes all the way back. It can start where the Cascades oval starts up by the word mantle. They're going to overlap.
oh, okay. Okay.
It's just going to extend way
How
down,
far? All down, all the way down
all
here?
the way down there. Yep. Perfect.
This is fun, Jeff.
I love this. So
Okay.
there are some figures like this on posters. I don't know if practical to share them in a live stream, but anybody who goes to look at some of the student posters will see these isotope diagrams and the contrast between the very narrow range of compositions that we see in the Cascade arc
Yeah,
compared to the really broad range we see in the Breakoff belt is striking.
that was beautifully done. Very, very good. Anything to add there?
Uh, no, I think all I would maybe add is that in order to be at the lower right-hand end, way down there where that has to be not just continental crust, but old continental crust,
Okay. Yeah.
because this ratio increases with time. So
Mm-hmm.
so that tells us that some of the Breakoff belt magmas were derived by melting of some crust that had old stuff in it. And that old stuff could be coming from Idaho. It could be, the early SWAC
Oh, yeah, yeah.
stuff that's coming from, the continental interior.
Right.
But it couldn't be coming from Siletzia or some, Siletzia derived sediment because that's young
Got
and
it.
it's not continental.
How do I spell this?
What are you trying to?
Stron.
Strontium.
Thank
Strontium.
you. Okay. Good job. That was
Thank you.
fun.
That was fun.
A couple final thoughts, and then I think we're done. And yeah, um, I had a thought 20 minutes ago before we turned on this Zoom camera, and I'm looking for a reaction. Drum roll, please. Is it possible that some of the Breakoff belt magmas have been offset by the Straight Creek Fault?
Yes.
even though the Straight Creek Fault is starting about the same time that the Breakoff belt stuff is happening, there's a lot
Well,
of time of offset on the Straight Creek to do this work.
um, one of the questions, so one of the students who worked, I believe, Wallenbrock, who worked on the Tatum Formation,
Okay.
um, I think that's the one that had been suggested to be an equivalent to the Teanaway.
Okay.
Anyway, one of the
Yeah.
units had been suggested to be an equivalent, and that was based on their composition, and they are similar in age.
Yeah.
Um, the conclusion, and I think this was Wallenbrock, came to was that they're actually not as similar compositionally as had been thought because he looked at a much greater suite of elements.
Okay. That's
But the other
cool.
thing to keep in mind was that although these two units are close together now, they might not have been so close together before movement on the Straight Creek Fault.
Spladam. So
Yeah.
this is literally right before I connected with you this morning,
Okay.
but we need 100 miles of restoration on the west side of the Straight Creek Fault. Like if I grab some scissors, all I'm trying to say is that if this is the Teanaway and the Frost Mountain and the Tainum, are are there extensions of the Teanaway? I know that the Teanaway comes right to Lake Cochise and then abruptly stops at the Straight Creek Fault. Like I remember shooting that video going, there's got to be some Teanaway on the other side. But today it's up across the border, I guess. I don't know if anybody's looked up there for breakoff belts that are now in southern BC, but that's kind of fun. And the same for our Summit Creek, basalt of Summit Creek at White Pass today. If we restore the Straight Creek Fault, we're suddenly now underneath the young cover in Oregon to find
Hmm. Right.
some of that. Um, I don't know how much to do with that, but we haven't even introduced the Straight Creek Fault really, but that's fun for me. And I don't know, you say one of your students thought a little bit about that, but maybe there's more that could be done to, if somebody's
Yeah. I
motivated.
mean, my student only thought about it from a geochem perspective, but Bob Miller or Mike or somebody who's thought a lot more about movement on the Straight Creek Fault and on, what units can be correlated on opposite sides may already know more about this, or
Yeah.
at least would have ideas of candidate units that ought to be scrutinized more to see if they are a match. Great
Very
idea.
good. Very good. Thank you. So, Saturday morning, December 21st at 8 a.m. Pacific time, viewers, if you happen to catch this before we do that, you're welcome to join us live. Are you going to be home and watching us live tomorrow morning, Jeff?
That's the plan, yes.
Okay, good. And I don't know if you're willing, Jeff, if you can be like this and maybe be available in case we want to pull you in live tomorrow. It would just be on Zoom. It would be the same thing we're doing right now, but it would be during the live chat. In fact, I don't know if I'm that nimble to get that figured out, how to do that quickly and send you an email during the live show. But I think what you just did, I'm going to use the hell out of tomorrow. So I think we've got what we need. And thank you for that. But just in case, I'm warning you, we might try to pull you on camera just in case we need you.
Okay.
Okay,
It's
great.
always an honor.
Likewise. Uh, hold the line. Let me hit this off button, and then we can talk
Okay.
just a touch more before
Okay.
we see. So
Sounds good.
thank you for your time, Jeff. Thank you.
Thank you.
Bye-bye.